Hi, welcome back to educator.com. Today we're going to talk about applications of exponential and logarithmic functions. At this point, we've got a good understanding of exponentiation and logarithms. In this lesson, we'll see some of the many applications that they have. Exponential and logarithmic functions have a huge array of applications. They're used in science, in business, in medicine, and even more fields. They're used in all sorts of places. There are far too many applications to discuss them all in this lesson, so instead we'll focus on working a variety of examples. We'll begin with a brief overview of some of their uses, some of the uses that we can see for exponential functions and logarithmic functions. Then we'll look at many specific examples so we can really get our hands dirty and see how word problems of this form work. Now, before you watch this lesson, make sure you have an understanding of exponents, logarithms, and how to solve equations involving both before watching this. We won't really be exploring why the actual nuts and bolts of this solving works, how this stuff works. We're just going to be launching headfirst in some pretty complicated problems, so you really want to have an understanding of what's going, because we're going to hit the ground running when we actually get to these examples. So previous lessons, really helpful here if you're not already used to this stuff. Okay, let's go. Applications of exponential functions. Exponential functions allow us to describe the growth or decay of a quantity whose rate of change is related to its current value. So how fast it's changing is connected to what it's currently at, right? So some examples of applications, and we can also see how their rate of change is related to its current value. Compound interest, right? The amount of interest that an account earns is connected to how much money is already in the account, right? If you've got $10,000 in an account, it will earn more than if it has $1,000 in the account than if it has $100 in the account. So this is an example of seeing how the rate of change is related to the current value of the object. Other things that we might see: depreciation, loss in value; compound interest, loss in value. Those are both used a lot in banking, in business, anything that's fiscally oriented. Population growth is used a lot in biology. Half-life, the decay of radioactive isotopes, shows up a lot when we're talking about physics. If you're studying anything in radiation, and understanding half-life is very useful, and many others. There's a whole bunch of stuff where exponential functions is going to show up. It's really useful stuff. Now, I've got a secret for you, so don't let anybody else know about this. Many exponential functions have their own formula. Things like compound interest is 1 plus the number of times that it compounds in a year divided, oh, whoops, this should actually be the other way around. It shouldn't be n over r. It should be r over n. The rate of it divided by the number of times it compounds to the number of times it compounds times the time. If you don't remember that one, remember our very first one on exponential functions described why that is the case. Population doubling, p, some original starting principal amount, times 2 to the rate that they double at, times t. Half-life, some principal starting amount, times 1/2 to the rate times time. However, if you forget all these formulae, right? So there's a bunch of different formulas. There's even more than just these, but it's sometimes possible to use the natural exponential growth model. You can sometimes swap out any one of these guys, any one of these more difficult to remember ones, for good old PERT. P, the original starting amount, times E, the natural base, to the R times T, where R is the rate of the specific thing that we're modeling, times time. R will change depending on what different thing you're doing. So even if you're modeling isotopes, you know, half-life in plutonium and half-life in uranium, you'll get very different R's because the plutonium and uranium will have different rates of decay. So you're not going to use the same rate R. So once again, if you're talking about half-life, the R here would be totally different than the R in our PERT if you would use the specialized formula. So the R for half-life of uranium using this formula would be totally different than the R for half-life using the PERT formula. But if you can figure out what that R has to be for PERT, the PERT form, from the problem, you can get away with using it instead. So there's a bunch of situations where you might not remember any one of these specialized formulas, but it can be okay if you have enough information from the problem to be able to figure out what R has to be. And there's lots of cases where that will wind up being the case. We'll talk about a specific one on example 2. We'll see something where we could get away with not knowing what it is, not knowing the specific formula, and still be able to figure things out by using this PERT formula. We'll talk about it in example 2 if you want to see a specific example of being able to use this secret trick. Why is this the case, you probably wonder? Why can you do this? How can you get away with using PERT when we've got all these special formulas? How can you swap out some exponential formula for just natural exponential growth, the PERT form? So the reason why is because this e to the r part, e to the r can morph into other forms. For example, let's look specifically at a possible half-life formula. So we might have p times 1/2 to the t over 5. So we can see this as p times 1/2 to the rate of 1/5 times time, right? That's what we've got there. So some principal starting amount times 1/2 to the 1/5 times t. So for every, say, 5 years, we have half of the amount there that we originally had. So how can we get PERT to connect to this? Well, if we use this very specific r equals negative 0.1386, well, it also turns out that that's the same thing as negative 0.6931 times 1/5. So we can have PERT, our PERT form right here. Well, we swap out, we know what r is, so we swap that in for our r, and we get p times e to the negative 0.1386 times time. But we also know that negative 0.1386 is the same thing as negative 0.6931 times 1 to the 5th. So if we want, we can break this apart into a negative 0.6931 part and a 1/5 times t part that we might as well put outside. So we've got e to the negative 0.6931 to the 1/5 times t, because by our rules from exponential properties, that's the same thing as just having the 1/5 and the negative 0.6931 together, which is the r that we originally started with. Now it turns out that e to the negative 0.6931 comes out to be 1/2. By this careful choice of r, we're able to get e to the r to morph into something else. We can get it to morph into this original 1/2, and now we've got this 1/5 here, so it becomes just p times 1/2 to the t over 5, which is what we originally started with as the half-life formula. So by this careful choice of r, and notice, the r here is equal to 1/5. The r here is equal to the very different 0.1386. We get totally different r's here, but by choosing r carefully, if we've got enough information from the problem, sometimes you will, sometimes you won't, you will have to know that special formula. But sometimes you will be able to get enough information from the formula and you'll be able to figure out what r is. So you can have forgotten the special formula. You can forget the special formula occasionally when you're lucky, and you'll be able to just use PERT instead. By choosing the right r for PERT, we morph it into something that works the same as the other formula. Now, of course, you do have to figure out the appropriate r from the problem, what we were just saying. You have to be able to get what that r is. And remember, it is the r for PERT, which may be, and probably is, going to be totally different than the r for the special formula that we would use for that kind of problem. But if you can figure out what the r is from the problem, you can wind up using PERT instead. Once again, we'll talk about a specific use of this in example 2, where we'll show how you can actually use this if you wind up forgetting the formula. Now, I want you to note, the above isn't precisely true. E to the negative 0.6931 isn't precisely 1/2. It's actually 0.500023, which is really close to 1/2, but it's not exactly 1/2. But it's a really close approximation, and it's normally going to do fine for most problems. It's such a close approximation that it will normally wind up working. And if you need even more accuracy, you could have wound up figuring out what r is just to more decimal places, and you could have used this more accurate value for r. Applications of logarithmic functions. Logarithms have the ability to capture the information of a wide variety of inputs in a relatively small range of outputs. Consider the common logarithm, base 10. So if we have log x equaling y, log x going to y. So over here, we've got our input is the x, and our output is the value y. That's what's coming out of log on x. So x can vary anywhere from 1 to 10 billion, and our output will only vary between 0 and 10. Really tiny variance in our output, massive variance in our input. Why is this happening? Because 1, well, that's the same thing as 10 to the 0, right? And 10 billion is the same thing as 10 to the 10, because we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0. So that's the same thing as 10 to the 0 to 10 to the 10. And because it's log base 10, it's the common logarithm, when log base 10 operates on 10 to the 0, we'll get 0. When it operates on 10 to the 10th, we'll get 10. And as it operates on everything in between, we'll get everything in between as well. So massive variance in our inputs, massive different possible inputs that we can put in, very small range of outputs that we'll wind up getting out of it. This behavior makes logarithms a great way to measure quantities that can be vastly different, things that can have really huge variance in what you're measuring, but we want an easy way to compare or talk about them, that we have to be able to talk about these things, that they come up regularly, and we don't want to have to say numbers like 10 billion or 9,572,000,000. We want some number that's fairly compact, that doesn't require all of this talking. So we use logarithms to turn it into this much smaller, more manageable number that makes sense and we can understand relative to these other things. Earthquake magnitude is one of the things that's measured on it. It's measured on the Richter scale, which is a logarithmic scale. Sound intensity is another one. It's measured in decibels, which is another logarithmic scale. Acid or base concentration is measured on the pH scale. We'll actually have examples about that in example 3, and that one is measured once again in a logarithmic scale, and many others. There's a bunch of other logarithmic scales when you've got a really, really large pool of information that can be going in as an input, but you want to be able to narrow that to a fairly small, manageable, sensible sort of range of values, right? 0 to 10, it's going to have lots of decimals when you evaluate log of 8,072,000,000. It's going to have lots of possible decimals to it, but it's going to be a fairly small, manageable number for thinking about. Logarithms will also show up in formulas that are analyzing exponential growth. Because if we're building a formula that's going to be connected to exponential growth, if we're trying to sort of break down and figure out what its power is raised, we're going to wind up having logarithms show up when we're solving it, so they'll wind up showing up in the formula as well. So logarithms show up in formulas for analyzing exponential growth. All right, let's get to some examples. Principal investment of $4,700 is made in an account that it compounds quarterly. If no further money is deposited and the account is worth $5,457.57 in 5 years, what will it be worth after a total of 10 years? First thing, what kind of formula are we working with here? Well, we've got compounding but not continuous compounding, so we go and look that up. It's principal times 1 plus the rate divided by the number of times that the compounding occurs, raised to the number of times that the compounding occurs, times the amount of time elapsed in years. So our principal investment here is P equals 4,700, and we know that at time 5, so at t equals 5, we've got $5,457.57. So $5,457.57 is equal to what was our principal amount, $4,700, times 1 plus what's our rate? That's one of the things we don't know yet. We don't know what our rate is, and that's why we're setting up at t equals 5 instead of just hopping immediately to the 10 years question. We need to figure out what our rate is first, so that's what we're figuring out now. 1 plus r over n. Our n is quarterly, so that is an n of 4, because it happens 4 times in a year in each of the 4 quarters of the year. So 1 plus r over 4 raised to the 4 times t. Do we know what t is in this case? We do know what t is, otherwise we'd have 2 unknowns to solve in one equation. It's 5, because we're looking at the 5-year mark. So we work this out, we get $5,457.57 over $4,700 equals 1 plus r over 4 to the 20th. Now at this point we'd probably be tempted, how can we use logs? How are logs connected to this? We could take the natural log of both sides, we could bring down the 20, but then we'd wind up having natural log of 1 plus r over 4. We're actually losing sight of a much simpler way. When we raise to a power, how do we get rid of powers? If we're trying to figure out what's in the base and the power is a known value, we just take a root, right? We take a root depending on what the power is. If it's squared, we take square root. In this case, we're to the 20th, so we're going to raise both sides to the 1/20th. We are taking the 20th root of this. So raised to the 1/20th. So that cancels out here, and we're left with 1 plus r over 4. We take the 1/20th root of the 1/20th power, which is also the 20th root of $5,457.50 divided by 4,700, and that comes out to be 1.0075. We subtract by 1 on both sides, we get 0.0075 equals r over 4. We multiply by 4 on both sides, and we finally get 0.03 equals our rate. So our rate in this case is a modest 3% return on investment. So now we can use this information to look at the 10 years. So at t equals 10. So at this point, we've got everything that we need to know except for the amount. So the amount is the unknown. We don't know what it's going to be worth, but we do know what the initial principal was, $4,700. We do know that it's 1 plus a rate of 0.03 over 4 quarterly to the 4 times our number of years is 10. So our amount is 4,700 times 1 plus 0.03 over 4 raised to the 40th. We work that all out with a calculator, and it winds up coming out to $6,337.24. And that is the final amount in the account at the 10-year mark. Second example, carbon-14 dating. All right, so first we're going to talk about the idea, and then we'll actually work on a specific problem. Carbon-14 is a radioactive isotope. So a radioactive isotope is an element that is an isotope, that is one version of an element that breaks down over time. It decays into something else. So it is something for a while, and then something happens, it undergoes fission, it breaks apart, and it turns into a different element. It is radioactive, it radiates something away. If you want to learn more about this, you can study either chemistry or physics to learn more about radiation. It's a radioactive isotope with a half-life of 5,730 years. It's created in the upper atmosphere by cosmic rays. So cosmic rays from the sun or other stars hit the top of the Earth, hit the atmosphere of the Earth, not the top of the Earth, hit the upper atmosphere of the Earth, and they create carbon-14 isotopes. Then these carbon-14 isotopes are absorbed by living organisms, that is, plants and animals. They get absorbed by trees through the carbon cycle, and then the carbon winds up getting into the animals that eats those trees and the animals that eat those animals that eat those trees. Any plant that's absorbing carbon will wind up absorbing this. Carbon dioxide will wind up absorbing this, so it winds up getting into, the cycle of biology. Now, carbon-14, there's a very small amount of this isotope, but it's going to make up a small but consistent amount of the carbon of any live organism. So it's a very, very tiny amount, but it's going to be a regular amount. As long as an organism is alive, it's going to continue consuming things, going to continue bringing carbon-14 into its body, so that amount will stay basically consistent throughout its life. However, once the organism dies, carbon-14 stops being absorbed. There will be no more carbon-14 pulled in because now, since the creature is dead, since the organism is dead, it's not pulling any more carbon-14 into its body. It's not pulling anything else into its body. Without the isotope being replenished, remember, carbon-14, it's radioactive, it begins to break down over time. So the C14, another name for carbon-14, in our dead organism will begin to decline because the creature is no longer pulling in carbon-14 to keep its levels consistent, so the carbon-14 begins to slowly drip away, begins to slowly dissipate, break down, decay into other things. This fact allows for carbon-14 dating, also known as radiocarbon dating because it's based on radioactive carbon, or simply carbon dating. By knowing how much C14 would be in a live organism, we know how much that is in live organism because we can just measure it on real live organisms. We can figure out this creature is alive, it's got this much C14 in it. So a live creature, something that was very recently alive or is currently alive, has this consistent amount of C14. Then, once the creature dies, it begins to steadily decline. So we can measure the amount in a dead organism, and since it's steadily declining, it's declining by rules that we know about, it's declining by half-life rules, we can figure out, based on the amount of carbon-14 left in the organism, left in the dead organism at this point, we'll be able to figure out when did the creature die, when did it go from being alive, keeping a steady state of carbon-14, to dead, where it's starting to let its carbon-14 just sort of disappear. So by knowing how much carbon-14 remains, we can get an estimate of when was the creature originally alive. All right, now we'll look at a specific example. Skeleton of an ancient human is discovered during an archaeological dig. If the level of carbon-14 in the bones is 7% of the carbon-14 ratio present in living organisms, how long ago did the human die? Then we want to round our answer to the nearest 1,000 years, and we're also reminded that the carbon-14 half-life is 5,730 years. So let's just start off. The general formula for half-life is the amount that we originally start with times 1/2 to the rate times time. Now in this case, the rate is going to be based on this 5,730 years. So our amount is going to be equal to P, whatever our original amount that we have of carbon-14, to the 1/2, and we want it to occur. We want a 1/2 to occur every 5,730 years, 5,730 years. So it's t divided by 5,730 years. That way, when t equals 5,731, we'll have an exponent of 1, and it will cause the half to go once. If it's 5,730 years twice, we'll have an exponent of 2, and we'll get 1/2 times 1/2, 1/4. Great, so that makes sense what's going on there. Now, what is our p going to be? So we probably want to figure out, well, what is the p that we're going to use? Well, notice it said level of carbon-14 in the bones is 7% of the carbon-14 ratio. So we were never given absolute values. We weren't given quantities of carbon-14. We were told ratios. So if that's the case, well, what would we want the amount to be when it's 0, when we start off at 0, when the creature was very first alive? So A equals p times 1/2 to the 0 over 5730. Well, that's going to be a number raised to the 0, which just becomes 1. So we've got A equals p. The amount that we start with is equal to the principal amount. That's exactly what it's there for. So what ratio do we want to start with? If the ratio slowly declines, let's just say that it started at a ratio of 1. So we'll say p equals 1. This is an idea that we're figuring out. We're saying, well, what would the ratio in a living organism be to a living organism? That'd be 1, right? So once the creature, just before the creature dies at 0 time, it's going to have a ratio of living organism to living organism, so it'll be a ratio of 1. The ratio won't have changed. So initially, this p thing is just going to be 1 because the ratio at the instant of death is just 1 because it's the normal thing with other living organisms. So our amount is 1/2 raised to the t over 5730. Now, at this point, we want to figure out what is the time that it took to get to where we are now. So at t equals question mark, we don't know what the time is, but when we have it at 7%, we know the amount is going to be 0.07, right? The ratio, if it's 7%, the ratio is 0.07, with what it originally was, 1/2 t over 5730. Now, at this point, we could take log base 1/2, but I just feel like taking natural log of both sides because we're going to have to do a change of base later anyway. So we've got natural log of 0.07 equals natural log of 1/2 to the t over 5730. So we can bring this down out front. So we've got t over 5730. Natural log of 0.07 will divide by the natural log of 1/2 on both sides equals t over 5730, which finally brings us to t. We multiply both sides by 5730 equals 5730 times natural log of 0.07 over natural log of 1/2. We punch that into a calculator, and we're going to wind up getting about 21,983 as our time, which we round to 22,000 years. This stuff isn't perfectly accurate because, so the creature died 22,000 years ago. Great. This stuff can't be perfectly accurate because there's always going to be a little bit of error in measurement, and since we only had 7%, that's not as accurate as 21,983, so it makes sense that we can only get to a certain amount, and that's why we're being told to round to the nearest 1,000 years, because we only have so much specific data here. Alternatively, if we had forgotten this a equals p to the p times 1/2 to the r times t, we could have started at the pert form. So the amount equals pert. So once again, the same idea, this p equals 1 business. Let's start at a ratio of 1. We can plug that in, so we've got a equals e to the rt. Now we need to figure out what is r. R is not going to be connected just directly to this 5730 years. Instead, what we know is at originally we have 0, originally at time equals 0, we have 1 as the ratio. So at time equals 5730, we're going to have 1/2 as the ratio. And that's our trick here. 1/2 equals e times e to the r times 5730. We can take the natural log of both sides, so we've got natural log of 1/2 equals r times 5730. We divide both sides by 5730. We've got natural log of 1/2 over 5730 equals r, which winds up getting us a rate of negative 0.00012097. Now, that's long, it's a little complex, but it does mean that even in the situation, the bad situation where we've forgotten the formula for half-life, how half-life works, we can still get something that's going to work. So now we've got this new thing we can work with. A equals e to the negative 0.0001297 times t. So with that in mind, we know that we can look at 0.07, put a little marker divider down here, 0.07 equals e to the same exponent, 0.0001297 t. We take the natural log of both sides. We got natural log of 0.07 equals negative 0.0001297 t, because exponent just comes down when we take the natural log. So now we can divide this natural log of 0.07 divided by this whopping negative, well, actually very tiny, but very long number, 0.0001297 equals t. We punch that into a calculator and we wind up getting that t is equal to, approximately equal to 21,982, which is very, very, very close to 21,983. So it winds up making sense that the reason why it's not quite the same is because we wind up having to use a decimal approximation. R wasn't exactly equal to negative 0.0001297. It was really close. It was approximately equal to that value. So we got something that was approximately the same thing as our answer. And in this case, we're still going to wind up rounding to 22,000 years as our final answer. Cool. Third example. First, let's talk about the pH scale. The acid or base level of a solution, acid and base are sort of two opposite ideas, in a solution is the concentration of hydrogen ions, positive hydrogen ions that are in solution. This concentration is measured in moles per liter, and moles is just a way of measuring how many of an atomic object you have. Moles per liter, which is called molarity. And it can vary hugely from one solution to another, so it makes sense that we want to use a logarithmic scale since it can vary hugely. To describe these massive possible differences, we measure acidity or alkalinity, acidity being the name for an acid measurement, how acid something is, and base, basic, alkalinity, alkaline, these are all same thing for how basic something is, how base is a solution, with a logarithmic scale, the pH scale, which comes from powers of hydrogen, which is connected to the fact that we're looking at a logarithm of our amount of hydrogen ions. If we denote the molarity of hydrogen ions with the symbol H positive, the pH value is pH equals negative the log, common log, so it's a base 10 log, of the molarity of hydrogen ions. Okay. With this idea in mind, we can now look at some interesting things. The pH of cow's milk is 6.6, while tomatoes have a pH of 4.3. How many times more hydrogen ions are in tomatoes than milk? So first we'll look at milk. And for milk, we'll describe its hydrogen ion concentration with the letter M. So its pH was 6.6, and that's equal to negative log of M. We move the negative over, we get negative 6.6 equals log of M. We can raise both sides to the 10th, to the 10, to the 10. This cancels out, and we wind up getting that 10 to the negative 6.6 is equal to the molarity concentration of milk. Cool. Next, let's do tomatoes. Tomatoes, we'll use a T to denote their hydrogen ion concentration molarity. So we were told 4.3 is equal to negative log of T. Negative 4.3 equals log of T. Once again, we raise them both up with a 10 underneath, so we get 10 to the negative 4.3. We keep the same color there, just so we see what's going on. 10 to the negative 4.3 is equal to, and remember, since 10 and common log, log base 10, they cancel out, and we're left with just T. So 10 to the negative 4.3 is the molarity concentration of ions in tomatoes, 10 to the negative 6.6 the molarity concentration of milk. So if we want to look at the ratio of tomatoes to milk, the ratio of ions in tomatoes to milk, so ratio of T to milk, well, then we just plug in the numbers we've got. We've got 10 to the negative 4.3 divided by 10 to the negative 6.6, which comes out to be 10 to the 2.3, which is about 200 times. So the ratio of hydrogen ions in tomatoes to the milk hydrogen ions in milk is 200 times more hydrogen ions in tomatoes than there are in milk. Now let's look at lemon juice. So if we've got lemons, and we'll use an L to denote it, then we were told 2.2 equals negative log of L. We'll use a curly L so we don't get confused with L in our logs. So negative on both sides, negative 2.2 equals log of our lemons. We raise both sides to the 10. That cancels out with the common log. So we've got 10 to the negative 2.2 is equal to the molarity concentration of hydrogen ions in lemons. So at this point, we can now compare lemon juice to milk and tomatoes. Let's compare it to tomatoes first. So ratio of lemons to tomatoes is going to be 10 to the negative 2.2 over tomatoes at 10 to the negative 4.3, which is equal to 10 to the 2.1, which comes out to be around 125 times. Really close. 126 actually is closer, but 125 times. So there's 125 times more hydrogen ions in lemons than in tomatoes. Finally, let's look at the whopping value that it is for milk versus lemons. So the ratio of hydrogen ions in lemons compared to milk is equal to 10 to the negative 2.2 divided by 10 to the negative 6.6, which comes out to be 10 to the 4.4, which is approximately 25,000 times. So there's 25,000 times more hydrogen ions in lemon juice than there is in milk. 25,000. So this is what we're seeing with the pH scale. It's a logarithmic scale. It's not just showing that there's a difference of, 4.4 between milk and lemon juice. We're showing this massive difference because we're being able to encapsulate this information of a huge difference with a fairly small number, being able to show that. Because we're using a logarithmic scale because there can be these massive differences in pH reading. All right, final set of examples, Newton's law of cooling. If you take a warm mug of tea outside on a cold winter day, the tea will cool down over time, right? It's in this cold environment, so it's going to cool down because it's warm and the outside is colder, so it's going to give off its heat energy to the surrounding environment. The surrounding environment is colder than it, so it will wind up sucking out that energy from our mug of tea. Conversely, if you put a warm mug of tea into a hot oven, we have this hot oven and we put the mug of tea in, it's going to heat up because the hot oven is a hot environment. It's hotter than the mug of tea is, so it's going to put heat energy in to the mug of tea. Our mug of tea will absorb heat energy from its surrounding environment. So if we've got a hot object in a cold environment, the hot object will radiate out energy and go to the cold environment. If we've got a cold object in a hot environment, it will pick up that energy and become hot, just like the environment it's in. The rate at which heat is transferred is proportional to the difference in temperature between the object and the surrounding environment. That makes a lot of sense. If you put your hand, your hand outside of a car window and it's, say, a warm day outside, a little cool, it's going to, cool off your hand slowly but surely. But if you put your hand out of a car window on a freezing day where it's colder than freezing, it's going to actually cause your hand to drop in temperature really, really, really quickly. So this makes sense. If something is put into a really hot environment, it's going to heat up faster than if it's only put into a pretty hot environment. The rate at which heat is transferred is proportional to the difference in temperature between the object and the surrounding environment. Since the amount of heat transfer is connected to a proportion of what this difference is, it winds up drawing on exponential equations. This idea is called Newton's law of cooling, and it's modeled by the temperature of the object is equal to the temperature of the surrounding environment added to the quantity temperature of the object's initial temperature minus the temperature of the surrounding environment times e to the kt. So this is the idea. The e to the kt is always going to wind up coming out to be, k will wind up being a negative number always in these cases when we're working these problems, because the environment is going to cause this part here to eventually drop down to 0 until eventually the object becomes the surrounding environment. It'll make more sense as we see some examples, so let's get started. Example 4. A pot of soup is on the stove at a temperature of 85 degrees centigrade when you turn off the stove. The kitchen is at 20 degrees, and after 10 minutes, the pot has cooled to 70 degrees. If the hottest temperature you can eat the soup at is 55 degrees, how much longer do you need to wait? All right, so let's figure out our things here. So what's the initial temperature of our soup? The initial temperature of the soup is 85 degrees. We were told that it started off at 85 degrees, so it starts off at 85 degrees. We're told that the kitchen is at 20 degrees, so the surrounding environment temperature is 20. Now, we don't know what the ratio is. We don't know what the proportionality constant is yet, and we don't know what the time is going to be in all of these cases. However, we do have one specific example at t equals 10. We know that it cools to 70. So let's look at that. So at time equals 10 minutes, we know that the temperature of our object is 70, and then we can set up everything else. The surrounding environment is 20, plus the initial temperature of 85 minus the surrounding at 20, e to the k, and we know that it's 10 minutes, t equals 10 in this case, so times 10. Great. We start working this out. We start working towards the e to the k times 10. So we subtract by 20 on both sides. 85 minus 20 in there becomes 65 times e to the k times 10. Divide by 65 on both sides. We got 50 over 65 equals e to the 10k. Take the natural log of both sides. So we've got natural log of 50 over 65 equals 10k, right? Because the e disappears when we take the natural log of both sides. We divide by 10 on both sides. So we got natural log of 50 over 65 divided by 10 equals k. And that winds up coming out to be k is approximately equal to negative 0.02624. So because of the fact that this proportionality constant came out to be negative, and it always will come out to be negative whenever we're looking at a Newton's law of cooling problem, because it came out to be negative, we're going to wind up seeing that this part here, as t becomes larger and larger, e to the negative larger and larger thing will become smaller and smaller, and this ti minus ts portion will get crushed down to 0 as the e to the negative thing becomes smaller and smaller. We'll crush that down, and we'll wind up being left at just the temperature of our surrounding environment. All right, let's figure out the other half here. So we want to figure out at t equals what do we wind up having a temperature of 55 degrees, because at that point we'll be able to eat our soup. So at 55 temperature, we know we'll have surrounding at 20 plus initial temperature was 85 minus 20 times e to our constant, negative 0.02624. I'll just leave that as k right now, and we can swap it out later when we need to figure out actual numbers. That's one trick to avoid having to do a lot of writing. So e to the kt. Subtract by 20 on both sides, we get 35 equals 65 e to the kt. Don't worry, we know what k is. We'll just plug it in when we get to needing it. 35 over 65. We can take the natural log of both sides in just a moment to get rid of that e. So we've got natural log of 35 over 65 equals kt. Divide by k on both sides, so divide by k. We can now plug that in, and we've got natural log of 35 over 65 divided by negative 0.02624. That's equal to our time, and that winds up coming out to be about approximately 23.6. So 23.6 minutes before, 23.6 minutes from the moment that we turn off the stove, because turning off the stove, when we turn off the stove, that was our time of t equals 0. So 23.6 minutes from the moment we turn off the stove is going to be the soup at 55 degrees Celsius. However, we were asked how much longer we have to wait. So we've already waited 10 minutes, right? Because at 10 minutes, we were told 70 degrees. So how much longer do we need to wait? So we need to wait 23.6, what we got here, minus the 10 minutes that we've already waited. So 13.6 minutes until the soup is cool enough to eat it. And there's our answer. All right, final example. This one's going to be a little bit of a doozy, but this is about as hard as you'll wind up seeing any of this sort of stuff get. All right, police discover a body in an air-conditioned room with a temperature of 22 degrees centigrade Celsius. When the medical examiner inspects the body at 10 p.m., it has a temperature of 33 degrees. At 11 p.m., it is at 31 degrees. When did the person die? And we're also told that human body temperature is 37 degrees. And finally, we're also told to give our answer the nearest tenth of an hour. All right, so what's the idea going on here? The police find this body, and so they can take the temperature of the body at one moment in time, and then they wait a little bit longer, and they can figure out the body has cooled. From that, they can figure out how fast the body cools, and because they know what it was at one time, they can go backwards. They can use the math to go backwards and figure out when was the body at a normal human body temperature. When was the body still alive? And because when it's 37 degrees, that'll be the moment of death. That will tell us when the person died. So this is forensic science. This is the sort of information, sort of math that crime scene investigators can use to figure out when did a person die by being able to create a good murder case based on that. All right, so let's get our pieces of data from this. We're told that the room has a temperature of 22 degrees. So the surrounding temperature of our room is 22. The initial temperature of our body is 37 degrees, right? Human bodies are 37 degrees when they're alive. When the medical examiner inspects the body at 10 p.m., it has a temperature of 33 degrees. So now we've got this confusing thing of time, right? In the last example, we knew what time 0 meant. We knew where it was, and everything was told relative to time 0. Time 0 was you turn off the stove, and then t equals 10 was 10 minutes from turning off the stove. But at this point, the t equals 0 is time of death, but we don't know what 10 p.m. is to that yet. But let's start off by saying t equals 0 is time of death. So the moment the person dies is t equals 0, and from there we just counting there. So t equals 0 is time of death, so t equals 1 is 1 hour after time of death. Because currently we're dealing with p.m., 10 p.m., our answer was told to be given in hours, so let's work with hours as our form here. So t equals 0 is time of death, so t equals 1 is 1 hour after death, t equals 2 is 2 hours after death, t equals 3 is 3 hours after death, etc., etc. Now, that still doesn't quite tell us what 10 p.m. is, so we're going to have to name symbols for this. So let's say t sub 10 is equal to the hours to get from the moment of death to 10 p.m. And similarly, t sub 11 will be the hours to 11 p.m. Great. With all of these ideas in mind, we're ready to start working things out. So at time 10 p.m., at the time of 10 p.m., which we don't know how many hours it is after death, but we can still talk about it as T10, we know that the body is at 33 degrees at 10 p.m. So we've got 33 degrees at 10 p.m. is equal to surrounding temperature, 22, plus initial temperature, 37 minus surrounding of 22, e to the k T10, because that's our time, so T10. Okay, subtract by 22 on both sides, we get 11 equals 37 minus 22 is 15, e to the k T10. So we divide by that, we've got 11 over 15 equals e to the k T10. Finally, we take the natural log of both sides, and we've got natural log of 11 over 15 equals k T10. Now at this point, we go, shoot. There's two unknowns, and this is only one equation. Well, we're going to have to bring a little bit more information to the table. So let's look at the 11 p.m. hour. So at T11, right? That's not T equals 11, that's T11, which is just the name that we gave to the number of hours after the time of death when it gets to 11 p.m. So how many hours after death is 11 p.m.? So at T equals 11, we've got a temperature of 31 degrees at 11 p.m. So, sorry, not at T equals 11, at T11. We've got a temperature of 31 degrees. And then surrounding environment is still 22, plus initial temperature was still 37, minus 22, e to the k, and now we're using a time of 11, T11. So T11, once again, I want to just point out, it's not time equals 11. It's definitely not that. It's just we named this thing hours to 10 p.m. as T10, hours to 11 p.m. as T11. They could be 1 and 2. They could be 5 and 6. They could be 80 and 81. We don't know yet. We just came up with names for these things so we could start working things out. We can subtract by 22 on both sides. We'll get 9 equals 37 minus 22 is 15, e to the k T11. We can divide by the 15, so we get 9 over 15 equals e to the k T11. Take the natural log of both sides. Natural log of 9 over 15 equals k T11. Shoot! We've got, once again, two unknowns, one equation. And between all of them, we've got k, t10, t11. That's three unknowns, two equations. We need some other piece of information that will connect these things together. How is k connected to t10? How is T10 connected to T11? Of course. How is T10 connected to T11? Well, 11 p.m. is 1 hour after 10 p.m., right? To get from 10 p.m. to 11 p.m., you go up 1 hour. So however many hours after death T10 is, we know that if we add 1 to that, we'll wind up being at the 11 p.m. mark. So T10 plus 1 equals T11. This key realization will allow us to solve things. So we can plug this in over here. So we've got natural log of 9 over 15 equals k times T10 plus 1. So k T10 plus k. Hey, over here we know what k T10 is. It's natural log of 11 over 15. Let's bring back down this. So natural log of 9 over 15 is equal to k T10. We swap that out for natural log of 11 over 15 plus k. We subtract natural log of 9 over 15 minus natural log of 11 over 15 equals k. Now at this point we could just punch that into a calculator, or we could remember the properties that we know if we want to do a little bit less in our calculator. So that's natural log of 9 over 15 divided, because subtraction outside of logarithms becomes division inside, 11 over 15. So since we're dividing by 15 on the top and the bottom, they cancel out, and we're left with the natural log of 9 over 11 is equal to k. We take the natural log of 9 divided by 11 in our calculators, and we wind up getting negative 0.20067 as our constant for k. Our proportionality constant of k is negative 0.20067. Great! That means we can now take this piece of information right here. We know what k is. We slot that in over here. We've got natural log of 11 over 15 is equal to negative 0.2, sorry, I accidentally wrote an extra 0, negative 0.20067 T10. We divide by that. We've got natural log of 11 over 15 divided by negative 0.20067 equals T10. So T10 is equal to approximately, sorry, it comes out to be exact, well, not exactly, but we'll truncate it, we'll cut it down to 1.5, cut off some of those decimal places, we'll round it to 1.5456. So it comes out to be approximately 1.5456. However, they asked for the nearest tenth of an hour, so that winds up being about 1.5 hours. Now we want to know, what time did the person die at? When did the person die? Well, if at T10, that's the hours to get to 10 p.m. from time of death. So if it's 1.5 hours to get to T10, then that means death occurs 1.5 hours before T10. So we know that 10 p.m. is 1.5 hours after death. So if we go back 1.5 hours from 10 p.m., we get 8:30 p.m. as time of death. Great. And this idea right here, this is actually a basis for something that, real detectives, real medical examiners can use, this sort of idea of how these things work out. Math has a lot of really powerful applications, and this is just one example that's, something that's almost out of a detective story. All right, cool. We'll see you at educator.com later. This is the end of logarithms and exponential stuff, so we're going to move into a new topic. I hope everything here made sense, because it's time to get started on something else. All right, bye.